Welcome to the afternoon session of the last day. David Woodruff will give the first talk on memory bounds for the expert problem.
Okay, yeah, thanks everyone for coming and to the organizers for inviting me. This is a joint work with Vaidehi Srinivas, Neil Shu, and Samson Joe, who is also here. Okay, so what is the expert's problem? So this is a problem of sequential prediction. We have some number of experts. These are not necessarily experts, just people with opinions or algorithms, or there are many possibilities of what an expert means. And for this setup, what we have is a sequence of days, and on each day, each of the experts is going to make a prediction. We'll focus on binary predictions for the talk, so the results will generalize. So here, each expert is going to predict that it's going to be sunny or rainy on that day. We're going to look at the expert advice, and then we're going to make our prediction. And then we're going to see the actual outcome on that day. Was it sunny or rainy? And then the next day comes along, we're going to see the predictions of the experts. And maybe we have something in our mind. Maybe we think that one of these experts is reliable. We might follow that expert. So we're allowed to keep some state of what happened in the past. We make our prediction. We see the actual outcome and so on. Okay, so we're going to make no distributional assumptions on this problem, and we're going to judge the performance based on the standard notion of regret. So the regret is just the number of mistakes that our algorithm makes minus the number of mistakes that the best expert makes in hindsight. So we look in hindsight, we look at each expert, how many mistakes they made. We choose the one with the smallest number of mistakes. We take that difference and we divide by the number of days. Okay, so it's like the error rate on top of the best expert's error rate. Here, the red boxes indicate errors, right? So this day, the actual outcome was sunny. This expert is wrong. And so these indicate errors. Here, this red box indicates an error of the algorithm of our prediction. And you see that in hindsight, the optimal expert made one mistake. But our algorithm makes two mistakes. So 2 minus 1 divided by 4, the number of days, gives us our regret of 1/4. Okay. So formally, to set up the problem, we have n experts who are each going to decide on a binary outcome 0 or 1 on each of t days. And our algorithm sees the expert predictions and predicts either 0 or 1 on each day. We then see the actual outcome on the day, which is 0 in 0, 1. And we can use this information on future days. And we'll say the cost of our algorithm is the number of incorrect predictions. And the regret is just what I said, the number of mistakes we make minus capital M, the number of mistakes of the best expert, divided by t, the number of days. Okay, so this is all a standard setup. Applications of the expert's problem and ideas for solving that are used in ensemble learning, like AdaBoost, forecast and portfolio optimization, online convex optimization, much more broadly, and so on. And there are classic standard algorithms for this. So weighted majority due to Littlestone and Wormuth. The way this works is if an expert is wrong on a day, then we're going to penalize them by multiplying by a weight, okay, that's less than 1. So we start off with all of our experts with weight 1. And then we see on the first day that the actual outcome was sunny. This second expert predicted it to be rainy. So we're going to downweight by multiplying their weight of 1 by 1 minus epsilon. Okay, these other experts were correct, so their weights stay at 1. And this happens on each day. Okay, so every time an expert is wrong, their weight gets multiplied by 1 minus epsilon. Epsilon is a parameter. Okay, so classic analysis shows that if you run this, sorry, let me also say, how do you actually do your prediction? Well, a classic algorithm is the deterministic weighted majority. So what you do is on each day, you just add up all the weights that correspond to predictions of sunny. You add up all the weights corresponding to predictions of rainy, and you just choose the larger one. Okay, so on the first day, sunny has total weight 3, rainy has 1 minus epsilon, so you would predict sunny. And classic analysis shows that this algorithm has the following mistake or regret bound. The number little m of mistakes by this algorithm is at most 2 plus epsilon times the number capital M of mistakes of the best expert plus 2 divided by epsilon times log n. Okay, epsilon here is a parameter, so you can set it very close to 0, but you're still not going to get better than a 2 approximation for this deterministic algorithm. The proof is a very short and sweet potential argument. You just look at the sum of the weights. On the one hand, it's at least the weight of the best expert, so at least 1 minus epsilon to the number capital M of mistakes of the best expert. And on the other hand, it's at most 1 minus epsilon over 2 to the number little m of mistakes you make times n. Now, why do we get these bounds? I mean, the best expert is erring this number of times, so their weight gets scaled by 1 minus epsilon that number of times. What about the upper bound? Well, since we're doing a deterministic weighted majority, each time we make a mistake, at least half of the weight gets scaled by 1 minus epsilon. So the total current amount of weight gets scaled by at most 1 minus epsilon over 2. Okay, and that happens number of mistakes time, and we start off with total weight n. Okay, and just solving for the number little m of mistakes, you get this bound here. Okay, please stop me if there are any questions at any time. So in order to improve this 2 approximation, there's a classic randomized weighted majority or multiplicative weights algorithm, where instead of just following the majority weight, you randomly sample an expert proportional to its weight, and then you just output what that expert outputs. And you can analyze that algorithm, and the expected number of mistakes is 1 plus epsilon times the number m. Again, that's the number of mistakes of the best expert, plus order log n over epsilon. And yeah, so let me just summarize. This is all standard previous work. The weighted majority algorithm downweights each expert that is incorrect on each day and selects the weighted majority. It gets roughly 2 approximation. Randomized weighted majority follows an expert proportional to its weight. And if you set epsilon to be roughly 1 over root t, again, epsilon was a parameter, then you can show that the regret you get is roughly 1 over root t. I'm going to ignore log factors in this talk. Okay, so the question that we ask is, what if you're memory constrained? Okay, what if you're a streaming algorithm going through the experts? So you go through the expert predictions on a day, and you don't have much memory. And you need to make a prediction. And you store something, and you go on to the next day, and the process repeats. Okay, so how much space do you need to get low regret in the streaming model? And there are many applications where this number n is very large. Okay, so we can't afford to store a weight for every single expert. Okay, so there are applications where each expert might correspond to an algorithm exploring some landscape in an optimization problem. Maybe you have many different experts, and you don't want to store weights for all of them. Can you still get low regret? Without a memory bound, or without memory bound. Yeah, so that's standard. This regret is best possible with no memory constraints.
Can you repeat the question?
Oh, I'm sorry. The question was, just offline, not in the memory constrained streaming model, are the classic algorithms optimal? And the answer is yes. Yeah. Okay. So the streaming model, the one that we're going to consider, you can think of waking up on each day with no memory except from a note that you left your past self. Okay, so this is a cute slide that my co-authors designed. So you have some note from the past, say S bits of memory, then you stream through the predictions on a day, and we can even allow the algorithm to store all the predictions on a day, and as long as it has small space in the next when it goes on to the next day, our lower bounds will still apply. From an upper bound standpoint, we can actually just stream through the predictions of the experts on a day. Yeah, so we stream through the predictions, we make a prediction, we see the outcome, we update our memory, we fall asleep again, and we repeat, okay? Now, there are various notions of the streaming model. So there's the arbitrary order model, where you can think of an adversary choosing a worst case set of predictions, just a worst case input, worst case set of predictions, worst case set of outcomes, and arbitrary order. And then there's also a random order model, which is maybe more realistic in certain practical settings, where maybe the predictions of the experts and the outcomes are worst case, but the ordering of the days is randomly shuffled. Okay, so you can think of this maybe that the experts are drawing predictions from a distribution, and maybe the days are independently sampled from that distribution, and that would naturally lead to a random order. Okay, so we're going to look at both of these models. So just to get some into it, yeah, questions, yeah.
Do you make the prediction after seeing the predictions of all the experts at the end of the day, or you have to maintain a prediction throughout the day?
You see all the predictions. Should I repeat the question, or it's fine? Yeah, I can hear. Okay, so you only do it at the end of the day. You stream through the predictions, and then you make your prediction.
Yeah, so you said that you can assume that the algorithm actually sees all the answers of the experts in one go. But suppose if you constrain that, are you going to look at random order amongst those?
So our upper bounds will be constrained, that we just walk through the predictions. But so that's nice, because we don't have to store them all on a given day, which would be a lot of memory, like n memory.
Right.
But our lower bounds would hold even if you were allowed to store everything on a day. Yeah.
Sorry, are you measuring quality over one day or over over the sequence of n days?
It's a sequence of t days. So on each day, you're either right or wrong.
Yeah.
And you're counting the number of mistakes across days.
Yeah, but the streaming algorithm doesn't have to be helping find the best expert for a given day. You are amortizing over t days.
Yeah, in fact, our streaming algorithm might never find the best expert. It's going to guarantee that it has a small number of mistakes across all days. Yeah. Any other questions? Okay. Yeah, so, okay, so just to get some intuition, can we just try to find the best expert and then just follow that best expert forever? And unfortunately, this requires omega n memory. There's a very simple reduction from the set disjointness problem. So I'm sure many of you know this problem, but what is it? So Alice has a set X, which is represented as a characteristic vector, n-bit vector, and Bob has a characteristic vector Y. And the promise is that either these sets are disjoint or they intersect uniquely. Okay, and Alice and Bob are going to talk to each other, and they want to figure out which case they're in, and this requires omega n communication, even for randomized protocols. And the reduction here, it holds already for 2 days. Okay, so you can think of Alice as being the first day, and Bob as being the second day. And what Alice does is she has her X, and the ones in the bits that are 1 in X are the experts that are correct on the first day. And Bob has Y, and the bits that are 1 in Y are the experts that are correct on the second day. And the best expert will make no mistakes on either day if set disjointness has an intersection, if there's a 1 on both days. Okay, so if you want to find that best expert, then you're finding the index where there's an intersection in set disjointness. And that's actually as hard as set disjointness itself. Okay, so Alice creates this stream. So each element of X is an expert that is correct on day 1. Bob creates a stream so that each element of Y is an expert that is correct on day 2. And they just run the streaming algorithm. If I could find the best expert, I find this index I of that expert. And I can also just verify if that's an intersection with a little bit of expert communication. And so I I have an omega n lower bound for that problem. So that's the starting point, and it might look bleak, but the thing is, this is not the end of the story at all, because a low regret algorithm need not find the best expert. Okay, so take that previous example where I had 2 days, and imagine I copy Alice's input t over 2 days, and Bob's input t over 2 days. Okay, if they intersect, there's one expert that's correct on all the days. I don't really need to find that expert. What I can do is, at the very first few days, I find an expert that's going to be keep outputting 1 on the first t over 2 days, and I just follow that expert. And then at some point, I notice that this expert starts making some mistakes, around the t over 2th day. And then I switch to another expert, and then that expert's correct on the second t over 2 days. And I'm only incorrect on a very few days, and I have no idea who the best expert is. Okay, so the question is, can you get better algorithms without finding the best expert? And these are our results. So the first result is a lower bound. We show that any algorithm that achieves regret delta, and think of delta as less than a half here, sort of 1/2 regret you would just get by random guessing. So we're going to say delta is less than a half, achieves this with probability at least 3/4, must use n over delta squared t memory. Okay, so let me put this in perspective here. Delta is the regret, right? We said even offline, the best possible regret is delta's square root 1 over t, square root log n over t. Okay? If I plug in delta's square root 1 over t, then it's saying that to get that optimal offline regret, I need omega n memory. Which, so n memory is not what I want to use in the streaming model if n is very large. But it doesn't rule out the possibility that if delta is, say, a constant, maybe I can get n over t memory and some significant but small constant regret. And this is useful if the number t of days is large. Okay, so but this is a lower bound, and this lower bound holds for arbitrary order, random order, and even this IID model that I alluded to earlier. I won't define formally. Okay, what about upper bounds? So we show a matching upper bound up to log factors in the random order model. Okay, so we show that there's an algorithm that uses n over delta squared t memory and achieves regret delta for any delta that goes down to this information theoretic optimum, best possible in the offline setting. The algorithm doesn't need to know hyperparameters or things that it shouldn't know, like it doesn't need to know the number m of mistakes of the best expert. And yeah, if you do set delta to be 1 over root t, it's not a very interesting algorithm, but for larger delta, it gives sublinear memory. There's also a connection to update time as well. So this might actually be more important in some applications. So standard offline algorithms, they maintain a weight for each expert, and they might have to update all of the weights in each iteration. We can actually get, so that's n time per iteration. We can also get this amount of time per iteration, which could be useful. I'll explain that more later. So this result extends to general costs, but I'm not going to describe that here. Okay, so what about the arbitrary order model? So here we don't have a complete answer. So it's a nice open question, but what we get is sublinear bounds. So if the number m of mistakes of the best expert is at most delta squared t over log factors, and delta is at least the information theoretic minimum, then we can get n over delta t space. Okay, so let me parse this for you. If delta is a constant, small constant, this is just saying the number of mistakes of the best expert is not really constrained, right? It can be almost as large as the total number t of days up to polylog factors. And we get n over t memory in that case. If delta is like 1 over root t, then the number of mistakes of the best expert is polylogarithmic, and we get n over root t memory in that case. Now, you might be a little bit confused here because I just mentioned a lower bound of n over delta squared t. And now I'm giving you an upper bound of n over delta t. And you know, delta is something small, right? So this upper bound is actually smaller than the lower bound. What's happening? Well, we've constrained the number of mistakes of the best expert to not be too large. Right, so one sort of consequence of this is that the hardness in the lower bound is actually coming from the case when the number of mistakes of the best expert is large. And we can actually show an n over delta t lower bound in this regime, but it doesn't quite match our assumption here. It needs m is less than delta t instead of delta squared t. In any case, I won't get into the details there, but there are a lot of questions here. You know, what can you do for larger m? Yeah, so let me just, remaining time, give you a glimpse of the techniques here. Yeah, so here is the lower bound again of n over delta squared t. And the lower bound comes from a reduction. Yeah, question. Okay, yeah.
So should we understand this as if you want to get a mistake rate comparable to the best expert, then you can do better? And the hard case is when the mistake rate of the best expert is high and you just want to do a little bit worse.
Yeah, I mean, yeah, up to quantitatively describing it, that's accurate, right? So this theorem, it doesn't say anything when the number of mistakes of the best expert is larger than that. Yeah. Okay, so we use communication complexity to prove a lower bound here. We define what we call the distributed detection problem, abbreviated epsilon diff dist. What we have are t players, each holding n bits. Okay, if you want to guess at how the reduction is going to work, each player is going to correspond to a day. And each player is going to have the n predictions of all n experts on that day. Okay, so don't confuse players with experts. Players are days here in this communication problem. And this problem is defined in a distributed setting. So we have a no case. In the no case, every bit of every player is drawn IID from a fair coin toss. Okay, not much interesting is happening there. In the yes case, what we do is we have an index L. One of the n, so we have n bits, right, on each day. And so there's some index L corresponding to one of these n bits, so that if you look across the t days, this is actually drawn from a biased coin. Okay, so the probability that it's 1 is 1/2 plus epsilon. Okay, and all the other coins are independently random. Okay, you want to distinguish which of these two cases you're in with low communication. Okay, now what does communication mean? So the players are going to talk to each other. The lower bound holds in the Blackboard model. So even if a player posts its message on some Blackboard that everyone else can see. Yeah, so how would you solve this problem? Yeah, so this is the problem, right? So the players, again, are the days, and each player has the predictions on a day. This is a no case where everything is random. In the yes case, we plant one of these coins that's slightly biased to being heads. Okay, we want to distinguish these two. Questions? Okay. Yeah, so how would you, just to get a feeling for this, what is a natural upper bound? So natural upper bound would just be to sample 1 over epsilon squared log n days, just exchange all of the predictions on those days. And that's enough to distinguish a biased coin of 1/2 plus epsilon versus unbiased coin. The log n is for the union bound across the n bits. And so how much total communication is that? Well, you're sending all n outcomes on 1 over epsilon squared days. That's n over epsilon squared. Okay, can you do better? Yeah. Yeah, sorry. So this is a multiplayer communication game. So there are T players. Each player is a day. It's going to be a day in the reduction, okay? So I haven't actually described the reduction yet, but just think of the communication problem for now. Okay, so there are T players. Each player is going to have n bits. Okay, and so the players want to know, and they're flipping these bits from the same coin, right? So in the no case, all of these are fair coin tosses. They're all independent. In the yes case, one of these coins is slightly biased to being heads. We want to figure that out. And so these players, they have to talk to each other to figure that out. And one protocol that we just said is, well, the first 1/epsilon² players can just post all their inputs on a blackboard, and then we can figure out if there's a biased coin. Okay, yeah, so that's that protocol, just sampling players and checking if there's a biased coin. And what we show is that it's actually best possible, okay? So there is an n/epsilon² total communication lower bound, even in this blackboard model. Okay, so there isn't some way of cleverly sketching or compressing your input to beat this simple sampling protocol. What is the intuition behind this? Well, sort of intuitively, we know we need 1/epsilon² samples to distinguish a biased coin versus an unbiased coin. And intuitively, the players roughly need to solve this single coin problem on each of n coins. So you might think, well, maybe n should multiply 1/epsilon². And that's roughly the right intuition. So you're not solving all the n copies. You're really just solving the OR of n copies. You want to know if one of them is biased. And this sampling lower bound, of course, does not translate into a general communication lower bound. But you can use technology to formalize this intuition. So using a direct sum framework of Baryosef et al., what you can do is look at the information that the protocol transcript needs to reveal about the inputs. Okay, and you break up the problem into n problems, one for each of these coins. And you can use a direct sum theorem for the OR problem to show that the total amount of information the protocol needs to reveal is at least n times the amount of information it needs to reveal on one of these coin tosses. And technically, it's when the information is drawn from the uniform, when the inputs are drawn from the uniform distribution. Yeah, Piotr.
Are you using the order or the framework?
Yeah, so you can use this as a black box to reduce n problems to one problem. Yeah. You're measuring information under this no distribution, and this is coming from their theorem of that's how it works when you're solving an OR of n problems. Okay, so we reduced the problem to showing an omega 1/epsilon² information lower bound for one of these problems when the information is measured with respect to the no distribution. But the protocol, of course, needs to be correct on a different distribution. The distribution which is, say, half the time it's biased at 1/2 plus epsilon and half the time it's uniform. And you can show a 1/epsilon² lower bound for this using so-called strong data processing inequalities. So originally, Ducci et al. Had a work on this, which works for one-pass streaming algorithms, which is actually all we need here. This was strengthened to multi-pass in higher dimensions by Garg et al. Hui is here. And follow-up work in the sparse setting by Braverman et al. That I won't describe. But the idea is really to combine these. And you do need just a little bit of work to make sure the information is measured with respect to the no distribution, but you can do that. And yeah, putting those together, we get an n/epsilon² information and therefore communication lower bound for this problem. Okay, how do we use it for our problem? For the experts problem. Well, remember there's this problem, right? With set disjointness, it was a very hard communication problem, but it was kind of easy to get low regret, right? You didn't actually have to find the best expert. So do we run into similar problems here? Okay, so let me, so the reduction is, we want to try to set up this communication game to capture the experts problem. So we want to distinguish whether there is this slightly biased coin or not. Okay, and here is a challenge. Well, here's my nice input to the communication problem, right? Every day here is one of the players of the communication problem. And these n bits on that day are whether it's sunny or rainy. And I'm trying to figure out if if there's a biased bit here. And what I do is I don't look at the input and I just always output 1. I always output it's sunny. Right? And if we're going to make 1 the actual outcome, then I'm always correct. I didn't look at the input. Of course, I didn't solve the communication problem. So how are we going to fix that issue? So we would like to use an online learning with experts algorithm for solving this communication problem, where we're going to set epsilon to be roughly this regret delta. However, as we saw, an algorithm could have good cost, low regret, without even looking at the communication problem. So to fix that, we're going to use a masking argument. So the outcome of each day is going to be masked by an independent fair coin flip on that day. And we're also going to mask the actual outcome on that day. So let me draw the picture to you. So here on the left is what we started with, right? You just always predict sunny, and you don't learn anything about this communication game. But instead, what we're going to do is this first player that corresponds to this first day is going to flip a random coin. And it's going to XOR all of the predictions of the experts together with the actual outcome on that day, right? So we started off with all the outcomes being 1, and now it's going to be 1 XOR the mask for that day. So here the mask was 1, so I flip everyone's prediction, and I also flip the actual outcome on that day. Okay, so you can think of this as the player as hiding information from the streaming algorithm. Because the streaming algorithm doesn't know the mask. The player knows it. Okay, and so what do you get here? Well, importantly, in the no case, actually everything is uniformly random. Because you're in this distributional problem. All the predictions are uniformly random. The outcome is uniformly random because it's 1 XOR a mask. Everything is uniformly random. So any algorithm is not going to achieve low regret, right? The best thing, any algorithm just by turn-off bounds for any delta, if there is no bias coin, if you're in this no distribution, no expert will do better than 1/2 plus delta over 3. No algorithm can do better than that because everything is just independent random coins. Okay, on all the days are independent, everything is independent. On the other hand, if there is a bias coin, then by doing this masking, I preserve the number of correct days of the best expert. Right, the best expert was 1/2 plus delta of the time it agreed with the output. Right, it was all 1s before the masking. The actual outcome was all 1s, and maybe I mask these on a day, but they still agree. And I mask them on the next day, they still agree. So there still is an expert that is correct, roughly 1/2 plus delta fraction of the days. And so the streaming algorithm, if it's going to have low regret, it actually needs to be correct better than it would be in the no case when everything was random. So what we can do is, in this reduction, we can look at how many times the streaming algorithm was correct. Okay, in the no case, the streaming algorithm is going to be correct, roughly 1/2 plus, say, delta over 3 fraction of days with high probability. Any algorithm is correct that number of days. And in the yes case, if the streaming algorithm is actually correct in getting low regret, there is a best expert, and so it has to be correct, at least 1/2 plus 2 delta over 3 days, say. And I can look at each day whether or not it was correct. This is minimal additional communication. and I can figure out if I'm in a yes case or a no case. Okay, so that's how the reduction works. Yeah, so the online learning with experts algorithm with regret delta must be able to solve this communication problem we defined, where the epsilon in that problem is order delta, and so therefore uses n over delta squared total communication. And so this translates to a streaming algorithm that uses n over delta squared t memory, because the state of the streaming algorithm is what is passed to the next state. Okay? Questions? Yeah. That's right. Yeah. Yeah. So in the no case, there is no good expert, and there's no good algorithm either. Everything is independently random. And so the algorithm is going to be correct, a half plus maybe delta over 3 fraction of the days. It's going to be very close to a half. There's no algorithm. In the yes case, there is a good expert. This masking preserved that expert's number of mistakes. And so the streaming algorithm has to be doing better. And we can, yeah.
David, if you could just say.
Oh, yeah, sorry, to repeat the question, it was just how to set up the communication game so that the streaming algorithm can solve it. Basically, that's what it comes down to, yeah. Any other questions? Okay. Yeah, so that's the whole n over delta squared t memory lower bound. And yeah, so I don't have much time. So I just want to give you a glimpse of how the algorithms work. And I'll start with arbitrary order. And let's look at the case when there are no mistakes. Okay, so if there are no mistakes, the best expert makes no mistakes. A natural thing to do is, well, what if we iteratively pick pools of experts? Okay, I'm going to choose the first k experts, and I'm just going to run a classic offline algorithm on them. And if I notice that those experts start doing really poorly, then what I'm going to do is I'm going to throw them away, and then I'm going to look at the next pool of k experts. And I'm just going to go through them deterministically, looking at k experts at a time. And at some point, I'm going to choose the best expert. I'm walking through them. When I choose the best expert, it makes no mistakes. I'll never throw it away. I'll follow them forever, and I'm happy. How many mistakes did I make? Well, it's roughly the number of pools I had to end up picking before I got to that best expert. So you can just, yeah, so that's the idea. We're going to choose a pool. When they start doing horribly, we're going to choose a new pool. And if we have a pool size of k, then we're going to have roughly n over k pools until we find that best expert. Each pool, if we're running one of these majority and halving algorithms, what it means is we're going to make log k mistakes on that pool. And so if we have n over k pools, each one making log k errors, we set that equal to the number of mistakes we want, which is delta t. We solve for k, the pool size, and we get roughly n over delta t. Okay? And the pool size really is our memory, right? We're just maintaining weights for everything in the pool. So right now, this is just deterministic. I choose the first k, and when the weighted majority algorithm throws them all away, then I have the next k and so on. Yeah, so what is the intuition? If the number of rounds is small, so each round is picking a new pool, then it means, well, the pools must have done well, right? Because you didn't throw away all the experts. So who cares? Maybe you didn't find the best expert. You did well. And the number of rounds cannot be too large because at some point you would actually choose the best expert and retain it because it makes no mistakes. Okay, so what if the best expert makes a small number, capital M, of mistakes? Well, this is the same kind of thing as before. You can iteratively walk through pools of experts. You might throw away the best expert now, but you'll throw it away at most m times. So you'll walk through the pools m times. And you can do the same calculation. Each time you walk through a pool, you pay, you throw away a pool, you pay log k errors. You set nm over k log k to be the number of errors. Anyway, you solve for the pool size. It grows linearly in the number of mistakes of the best expert, which is not great if that is large. So a natural fix is, well, what if we randomly sample pools? Okay. Now, it's still going to take us a bunch of pools if we're sampling pools of a certain size until we actually sample the best expert. But what might go wrong is we sample the best expert and they're doing really poorly on the day when we sampled it. And then we throw it away, and then we have to wait a long time until we sample the best expert again, and so on. So we cannot guarantee the best expert is retained. So again, the intuition behind all the algorithms is if the number of rounds is small, the pools must have done well, so the regret is small. And the number of rounds cannot be too large because we want to eventually sample the best expert and hopefully retain it. And what we use, I'm almost out of time, so I'll go fairly quickly here. What we use is in the arbitrary order model, we use this bound on the total number of mistakes the best expert can make. Okay, so let me just draw this picture here. These x's, these boxes correspond to days. These x's are days where the best expert made a mistake. What are these yellow regions? Well, these are days where if we were to sample the best expert on that day, we would end up throwing away the best expert because locally they look pretty bad because they're going to make, it's like a dense region of mistakes of that best expert. But there can't be too many of these yellow boxes either because the number of x's, the number of mistakes is small. And you know the number, sort of, the density is like I pay a 1 over delta factor if I'm like delta fraction of the time wrong, which is when I would throw away that best expert. And so if I multiply the number of mistakes by roughly 1 over delta, that gives me the total number of bad days, meaning a day for which if I were to sample the best expert on that day, I would throw it away. And there aren't too many of those. Okay, so we just show that we have enough resamplings so that we're going to end up with good probability actually sampling the best expert on a day where we won't throw it away. That's the arbitrary order algorithm. Now I'm really out of time. Let me just give you the, by the way, the analysis is kind of hairy, right? We have no idea what the distribution on days where you're going to resample an expert is. It depends on the entire history and choices made. So all we're saying is, we have enough resamplings to choose the best expert on one of those days. To get the better bounds for the random order model, that's the arbitrary order model, is just one main idea, which is that locally, everything behaves the same as it does globally. Okay, since it's a random order, the best expert, if it makes some total number of mistakes globally, then in any local region, it's also going to make that number of mistakes by concentration bounds of the random order. And this allows us to say when we sample this best expert, we actually won't throw them away. That's the main intuition. And I'm out of time, so let me just summarize. We gave a lower bound, this trade-off of n over delta squared t for delta regret. This was the memory. We matched that with an n over delta squared t upper bound for random order. For arbitrary order, we imposed a constraint on the total number of mistakes of the best expert, and we're able to get sublinear memory under that constraint. A natural constraint is if we can remove that restriction. A natural question is, can we remove that restriction? And also, how general is this framework, right? I mean, as I said, multiplicative weights is, the ideas there have been used for many problems in convex optimization, online convex optimization. Maybe these ideas are useful there. Let me, okay, it's not here. But let me just say that I did have some follow-up work that I can just quickly say that recently for deterministic algorithms, we were able to show you can't really do anything. So there's an omega n lower bound for constant regret that we think we can parameterize also in terms of the number of mistakes of the best expert. So these simple algorithms of iteratively walking through pools of experts deterministically seem to be optimal. We're still checking that. There are other questions that I get sometimes on this, which is, in online settings, you often allow the adversary to choose the input adaptively, right? It sees your previous guesses and chooses the next input. Can you get anything in that model? So the algorithms I described, they don't work in that model. Maybe the adversary kind of learns about the pool of experts that you sampled and can try to mess with you. But using some ideas from differential privacy, we're able to still get some non-trivial upper bounds. So instead of n over t or n over delta t, we can get something like n over delta root t. And yeah, we have no idea if that's optimal. And there's also some recent follow-up work of others that looked at the case when the number of days is much larger than the number of experts. And what are the sort of memory regret trade-offs in that setting? So yeah, that's all. Thank you.
Questions for David?
Yeah, Sash.
So do you think like in the low mistake setting, you can get a lower bound of n divided by delta t by exploiting the fact that like if you have a coin whose heads probability is delta and a coin whose heads probability is delta over 2, then you can distinguish those it requires 1 over delta samples to distinguish them. So can you combine that with your OR framework to prove a lower bound in that setting?
Yeah, we actually can prove an n over delta t lower bound in the low mistake regime. We just actually take our general lower bound for general t and set delta to be constant there.
Right.
And then just replace t with delta t. And then you actually get a n over delta t lower bound. But the issue there is still this constraint is m is less than delta squared t. And so you could hope for m is less than delta t there, and we don't have that. Yeah.
I remember at some slide you had log 1 over delta in some upper bound. It's not here in the summary. So anyway, where does this come from, like this log 1 over delta? Some concentration of measure or something else?
So that delta was probably the failure probability, not the, I don't know, there are log factors floating around. I mean, but yeah, I mean, one thing is, for example, in the random order model, for example, we would like that this local behavior to look global that I said. This happens with some probability, right? It could be that you randomly ordered the stream and voila, you got back, this worst case deterministic stream. But that happens with some low failure probability. And so then there's some failure probability for that goes into the algorithm. Does that?
Okay. I thought it might have been something else. Or.
Oh, okay. Yeah, I'm happy to talk to you more about it.
Okay.
Yeah.
So this pool of experts, isn't it like some sort of like meta expert? Like, is it like each pool of expert is itself an expert in some sense, right? So it's like.
Well, so we're only looking at that pool at a time, right? So it's not like we have like many meta experts and we're updating all of their weights. It's more like we're only looking at the experts in this pool at this time.
Right, but that's to evaluate whether the pool is good or not, right? Whether the good expert is inside that pool, right?
It's to evaluate whether the pool is good and also, to base our prediction on that day. We're only basing it on those experts. Those are the only experts that we're tracking weights for.
Right, but in order to find out which pool is good or not, like, can you see the pool itself as an expert that is like the concentration of all the experts, and that's kind of a meta expert, instance.
Yeah, you could imagine algorithms of trying to find the best expert by doing that, but we know that in general finding the best expert is hard, right? So
yeah, no, I'm saying like maintaining multiplicative weight update over the set of pools, and.
Yeah, but okay, then the question is, what do you output for that pool? Are you going to do like majority? I mean, yeah, so you have weights for the meta experts, and then what do you output in each of those?
Yeah, you have to define the loss function for the quality of the pool. I guess that's a...
Right. It's a good suggestion. I don't know if it improves bounds, Yeah,
okay, cool.
So if there are not further questions, let's thank David again.